Welcome back. In this video lecture, we will look at what is known as steric forces. It is also called as polymer-mediated forces. So far, we have looked at different types of forces, van der Waals forces, electrostatic forces, and what we have not covered in this module is steric forces. These are polymer-mediated forces. Whenever we deal with both polymer and colloidal particle mixtures, we will encounter interactions, right? Polymer and mediated interactions that will take place between polymer molecule and the colloidal particle surface. Okay, we will look at them in details. Okay, let's begin. Right. So first, let us look at the polymer-mediated forces. Nothing but, whenever we deal with polymer colloidal mixtures, what kinds of interactions do take place, right? That is exactly what we are looking at. Whenever we deal with this kind of a system, often we will encounter two kind of scenarios, right? Two possibilities will be emerging. One is nothing but what is known as negative adsorption, okay, and the other one is the positive adsorption, right? So the figures A, B, C illustrate the negative adsorption phenomena, whereas the figures D, E, F describe positive adsorption, right? Right. So negative adsorption occurs whenever the affinity between the polymer molecule and particle surface is not that great. When it is very poor, you expect the the negative adsorption. In such scenario, what will happen is polymer molecules will be excluded from the vicinity of the particle surface, which means that uh, you can see that they get segregated themselves into a separate phase, okay, because they don't share a great affinity between particle surface and polymer, among themselves. So you can expect that these polymer molecules get excluded from the vicinity of the particle surface, such that each uh, you know will be segregated into different phases. Okay. So what is the consequence of that? First is they generate a depletion layer. Okay. So depletion layer meaning certain volume, okay, will not be accessible by the polymer molecule. Say for example, because they don't share a great affinity around the particle surface, these molecules cannot freely move around, okay, because they share very poor affinity, right? So in such scenario, you can expect that the polymer molecules will will create a depletion layer, okay, from the vicinity of the particle surface, okay. And what is the consequence of that? So in such case, what will happen is, because some of the volume is not accessible to the polymer molecule, so they will try to push these particles, compress these particles so that they get more free volume, okay. So this process is spontaneous, and this is driven by entropic. This is a entropy driven energy minimization process. In this case, what happens is, because they don't share great affinity and they create a depletion layer around the particle surface, there will be a pressure imbalance, okay. There will be osmotic pressure imbalance because of this condition. So in order to get more accessible volume, this polymer molecule will push by these colloidal particles such that they get more free volume, right, more free accessible volume. So this is what going to happen whenever you deal with non-adsorbing polymer molecule. Remember, this scenario is applicable when you deal with non-adsorbing polymer molecule. So when the affinity between them is not great, right? Right. So what is the consequence of that will be, as I said, there will be depletion zone. So that will lead to depletion attraction between the particles, right? So how do we control this depletion layer thickness? So it depends basically on size of the polymer molecule. As the size of the individual polymer molecule goes up, the depletion zone itself will grow, right? So, so the size of the polymer molecule is characterized by what is known as radius of gyration. That is nothing but R suffix G, right? R suffix G is nothing but radius of gyration, which is again, um, uh, you know, uh, affected by molecular weight, right? So, because radius of gyration is proportional to molecular weight to the power 1 by 2. Again, molecular weight is also an important parameter that actually controls the depletion layer thickness. So, both Rg, which is radius of gyration, and molecular weight, both are important parameters in this depletion layer thickness, right? So, so as a result of which, what happens is, because of these depletion zones, the presence of these depletion zones, it leads to an effective attraction between the colloidal space. This is clear now. There is something called positive adsorption, right? The other one is positive adsorption. In this, the affinity between the particle and polymer will be great. Okay, in such scenario, so what will happen is, they will get adsorbed onto the particle surface nicely, right? So this is happen when the affinity between the polymer molecule and particle surface is great, right? So what are the consequences? So let's say you have three cases, right? One is you have got affinity is good, but polymer concentration is low. In such scenario, what will happen is, because they cover the particle surface partially, not completely, in such case, what will happen is, they will lead to bridging between the adjacent neighboring particles, right? Because this polymer molecule, which is anchored to one particle surface, will also get anchored to the neighboring particle surface. In this way, they will form bridging, right? So this phenomena is nothing but bridging flocculation. So in this case, the particle they get bridged, right, and they will exhibit elastic characteristics because of this bridging, and it can be regarded as spring-like objects as well, right? On the other hand, let's say if you have polymer concentration sufficient concentration, if you have concentration sufficiently to cover the entire particle surface, in such case, what you would expect is the steric stabilization, right? So the steric stabilization is because the polymer molecules are covered now, entire surface, the entire surface of the particle is now covered with the polymer molecule. The adjacent molecule with the same case, right? Because when these two particles approach each other, there will be steric hindrance, because the polymer molecules will act as a barrier, physical barrier. They will not allow the particle to penetrate any further, right, beyond some center to center distance. So in such case, you would expect steric stabilization. There is something, this scenario, figure F corresponds to case when you deal with higher concentration of polymer. In such case, what will happen, because when you have concentration which is slightly higher than what is required to completely cover the surface, this free molecule will go in between the neighboring particles. So they will form more like a network, like a structure, okay, because this free molecule can now get anchored to another polymer molecule. So they will form a network like structures, right? This scenario is uh, you know uh, this is more likely to happen when you deal with when you have higher concentration of polymer in the mixture, right? right. Now let's look at a different phenomena, right? So we just looked at what is known as bridging flocculation, steric stabilization, and depletion stabilization. Okay, so as you know, as we just now described, when at low concentration of polymer, you expect bridging to take place. That will lead to bridging flocculation. Okay, because this happens because there are, I mean, when there is no sufficient number of polymer chains to cover entire surface, because only because the polymer molecules absorbed on the surface partially, not fully, so they will lead to bridging flocculation, right? On the other hand, when you have sufficient number of molecules to cover the entire surface, you expect steric stabilization to occur. Okay, so in this case, these polymer molecules will act as brushes, right? So when they approach each other very closely, so they cannot penetrate any further. Okay, unless the you know force is applied from outside. From outside the particles, right? So these two particles cannot penetrate any further because of the physical barrier or steric hindrance, right? So this is nothing but steric stabilization. When you have polymer concentration, okay, from moderate to high, so you can expect depletion flocculation or depletion stabilization. So depletion stabilization occurs, uh, whenever in a good solvent, okay, because these molecules are absorbing molecules, right? This molecule, can be readily will be readily can be easily dissolved in the good solvent. So when you have higher concentration of absorbing polymer molecules, because these molecules can move around freely around the particle surface, the these particles, I mean these molecules will move around freely around the particle surface, so they will act as a shield for the particles, right? So they will create some sort of crowding effect. Okay, so because of which depletion stabilization can be expected, right? So one hand we saw uh, that there is something called depletion attraction, that is due to non-absorbing polymer molecule. The depletion stabilization is because of the absorbing polymer molecule. Okay, so uh, this happens in good solvent. Okay, because in good solvent the demixing process is thermodynamically unfavored, right? So hence you can expect depletion stabilization, because here the polymer molecule will have good affinity, okay, between themselves and the particle surface. They can easily move around the particles, so they will the particles will be surrounded by these molecules, so they act as a shield, right, or crowding effect, right? So what is good solvent? So good solvent meaning the polymer molecule is highly soluble, okay, and they remain in the expanded state rather than the collapsing or aggregating, right? So rather than in the rather than being collapsed or aggregated. So here let us look at the difference between grafting and adsorption. So grafting is due to the covalent bonding, so which is permanent. The adsorption is due to the non-covalent interaction, or you can say physical interaction. Okay, whenever the affinity between the polymer molecule and the surface is good, they will get anchored onto the surface. In the case of grafting, it is purely due to the covalent interaction. Okay, so because it is covalent interaction, the chain, it doesn't offer a good chain flexibility. But in the case of adsorption, it offers a good chain flexibility. Okay. Um, so when it comes to adsorption, because it is adsorption process, it is due to energy minimization, and energy minimization is entropy driven. The energy minimization process is entropy driven in the case of adsorption. Why? Because it undergo different configurations like loop like configuration, train like configuration, and tail like configuration. In this scenario, the energy minimization is because of the entropy. Okay. Whereas in the case of the grafting, you don't expect any energy minimization because this is already anchored onto the surface because of the covalent bonding. And so because this is that there is a chain flexibility and all that, in the case of adsorption, it can be controlled by the it is sensitive to pH and ionic conditions in the solution, whereas in the case of grafting, it is less responsive to environment. So you can expect bridging in the case of adsorption, especially when tail-like configuration is favored and concentration is too low. Okay, in such scenario, you expect bridging. In the case of grafting, it produces brush-like structure. Okay, and this brush-like structure will always lead to steric stabilization, provided the grafting density is meaningful. Okay, right. So here we will look at the configurations, the various configurations in details. So as we described just now, the loops and trains, okay, uh, you know, both are one and the same. But in the case of train, the polymer molecules anchor onto the surface, in a continuous fashion, okay, such that they orient themselves in parallel to the surface or lie flat on the surface, which will ensure more strong adhesion and anchoring, right. So this will always lead to steric stabilization. Both train like configuration and loops like configuration both lead to steric stabilization. Okay. So in the case of loop, it leads to, I mean, the polymer molecules anchor at multiple points on the surface, and it will exhibit U-shaped orientation. Okay, and this will also lead to steric stabilization. Okay, but in the case of tails, in contrast to loops and trains, when it assumes tail-like configuration, okay, basically this is nothing but configuration, when it anchors onto the surface at a single point but extends freely into the surface, the solution, which means that the rest of the segments will protrude outward from the surface into the bulk solution. In such scenario, you expect bridging and or bridging flocculation, because this tail can again get anchored onto the surface, okay, neighboring particle or neighboring surface. Okay, so these are various configurations. We expect steric stabilization when it comes to loops like or trains like, and we expect bridging flocculation when it assumes tails like configurations, right. Yeah. So here we'll look at the little bit more about the interaction energy. See, whenever the particle surface is covered with polymer molecule using covalent interaction, you expect always steric stabilization. Okay, but provided the grafting density is too good. If grafting density is poor, we can't expect steric stabilization always. Okay, but on the other hand, whenever the particle surface is covered uniformly with polymer molecule via adsorption, okay, in such scenario, one would get either steric stabilization or bridging flocculation, okay, depending on the the concentration of the polymer chains on the surface. Okay, if the polymer chain, if the concentration of the polymer segments on the surface is too good, we expect good stabilization due to steric hindrance. Whereas in the case of if the concentration is too low, we expect bridging flocculation. Okay, right. Sometimes you can also tune the the bridging flocculation by increasing the steric repulsion. By tuning the molecular weight of the polymer. So let's say if you choose slightly higher molecular weight polymer, the longer chains create more thicker layers on the surface. So this will ensure that there is more steric repulsion. Okay, in such case you would expect steric repulsion to be more dominant than the bridging flocculation. So you can see that the interaction energy between the particles, right, surface to surface, as a function of surface to surface distance. So in the absence of the depletion attraction and bridging flocculation, when there is a steric hindrance, you would only expect repulsive force. Okay. In this plot, the positive y direction represents the repulsive force and negative y direction represents the attractive force. So in the case of the steric hindrance, we will only get the repulsive force. Okay, right. Whereas on the other hand, in the absence of steric interactions, especially when there is a depletion attraction or bridging flocculation, you the interaction energy follows the dotted line, right. So the interaction energy varies as a function of surface to surface distance as shown in the dotted line. So there will be attraction will as well. Okay, because of the absence of steric interactions, right. So this is all about the steric forces, or you can say polymer mediated forces. What is very important for us is when you can expect steric stabilization, when we can expect bridging flocculation. Okay, I think these examples would have given you enough insight into the steric forces and polymer mediated forces of interaction. We will stop here. We will continue from the next lecture. Thank you.